predicting likely basic graph shape from a quick visual inspection. Two subclasses of square root functions, one being y equals to the square root of a linear expression in x, and the second being y equal to a quadratic expression in x. Alright, first of all, a caveat. This lesson discusses a method for predicting basic graph shape. It's performed mentally and makes a likely conclusion in about 5 seconds once you have a little practice. By contrast, a detailed graph shape analysis would be performed on paper using algebraic steps, takes several minutes before you've ironed out all of the details. Okay, so again, we're looking for here a quick basic graph shape conclusion that takes us like 5 seconds to perform. Alright, first we have this generalization, and we have used it in previous vids, and that is that the graph of the function of the form y equals to a linear expression in x, that will be a semi-parabola having a horizontal axis symmetry, and the x-coordinate of the vertex is the solution to radicand equals 0. Here's example 1. So what will be the likely basic graph shape of y equals to the square root of 4 minus 5x? Alright, immediately you note this is a y equal to square root of a linear expression. You're thinking it's going to be a semi-parabola having a horizontal axis symmetry. You can even mentally compute the x-coordinate of the vertex by solving 4 minus 5x equals 0 in your head. Let's see, that would be 5x equals 4, x equals 4 fifths. And the y-coordinate of the vertex, well, that would be 0 then. Okay, and how's it look? Just like we thought. There we are, semi-parabola, horizontal axis symmetry, vertex at 4 fifths, comma, 0. Okay, on to the more complicated situation. What about making a quick analysis of the graph of a function having the form y equals to a quadratic expression in x? Well, first of all, it'll likely be one of a semicircle, or half an ellipse, or half a hyperbola. And what you do is you realize that by squaring both sides of this y equals to quadratic expression x, you've got yourself a y squared equals to a quadratic expression in x, which is reminiscent of all your conic sections. So you can think of this radical as basically cropping a conic section to half its original graph. Alright, let's take a look at a few quick examples of y equals to quadratic expression in x and confirm at least this first statement is sensible. And here's a y equals to square root of a quadratic expression. Notice the graph happens to be a semicircle. Second example, the function there, y equals to the square root of that quadratic expression, and this graph turns out to be a semi-ellipse. By the way, half an ellipse is a very general term. If you say semi-ellipse, that's considered by many people to be a half an ellipse which contains the endpoints of the major axis, like you're seeing here. Okay, here's another y equals to square root of quadratic expression in x kind of function, and this is also half of an ellipse for a graph. Alright, now there's a little difference between this one and the previous one. This half of an ellipse contains the endpoints of the minor axis. So what you could say is this is a semi-ellipse containing the endpoints of the minor axis. And probably best to avoid just flat out saying this is a semi-ellipse, because that has people expecting to see the endpoints of the major axis. Now again, in our quick 5-second claim of basic graph shape, we don't distinguish between whether it actually is a semi-ellipse or one that has the endpoints of the minor axis contained within it. We just conclude half of an ellipse, and that's the idea of a quick basic graph conclusion. Alright, here's another y equals to quadratic expression in x. Now here you see half a hyperbola. Now specifically, turns out to be a single branch of a hyperbola. And then we could look at this function. Here's a y equals to quadratic expression in x. This is also half a hyperbola, although it's a different kind of half. This half would consist of a pair of semi-branches, as opposed to that previous one, which consisted of a single branch. Now, making a quick basic conclusion about a graph shape, you don't distinguish between whether it's going to be a pair of semi-branches or a single branch. You are going to have a conclusion that is just simply half of a hyperbola. Alright, so how can this be done? Well, the reason this is doable so simply is that the graph of this sort of function, after you square both sides of this equation, everything is dictated by the x squared and y squared terms. And you just do a simple mental process, which goes about like so. First, you do square both sides, and then ignore everything except the x squared term and the y squared term. Then you'd mentally move the x squared term to the y squared side of the equation. Now you're ready to make a conclusion, and much of it falls back on your knowledge of conic sections. If you have the x squared coefficient and the y squared coefficient being equal, that would first of all remind you of a circle, and then that radical is basically cropping you down to half, which brings you to a semicircle conclusion. Now, if the x squared coefficient and the y squared coefficient are unequal but have the same sign, that does remind you of the ellipse, but having the radical sign here crops you down to having half an ellipse is your conclusion. Third case, if the x squared coefficient and the y squared coefficient have opposite signs, that would be reminiscent of a hyperbola, and this radical sign here is going to crop it down to just being half a hyperbola as your conclusion. Okay, here come some examples, and these have been generated by grabbing the equations of those previously shown graphs. Let's start here. So, what will be the likely basic graph shape of this function here? Okay, first you notice, oh, this is a y equals to the square root of a quadratic expression. So, in your mind, you would first square both sides, just keeping track of the x squared and y squares. Then, move the x squared term to the y squared side. Now you notice that you have unequal coefficients, but have the same sign. So first you're reminded of ellipse, then the radical reminds you that it's going to be half an ellipse. That's what's expected here. Indeed the case. Okay, there's that semi-ellipse. Example 3. What will be the likely basic graph shape of this function here? Okay, you notice it's a y equals to square root of a quadratic expression in x. So you begin the mental process of squaring both sides, just keeping track of the x squared and y squared terms, moving the x squared term to the y squared side. Now you realize the coefficients have opposite sign. That reminds you of hyperbola. The radical crops half of it, so your conclusion is this will be half a hyperbola. Correct. Okay, example 4. What will be the likely basic graph shape of this function here? Okay, again you see a y equals to square root of quadratic expression in x. You begin the mental process, square both sides, keep track of just the x squared and y squared terms, move the x squared term to be on the y squared term side. Now the coefficients are equal. This reminds you of a circle. The radical will crop half of that. Now you've got a semicircle conclusion, and it's correct. Incidentally, it might not be a bad idea to, as almost a separate part of your memory, keep track of this, maybe the special case of y equals to r squared minus x squared as being the graph of a semicircle, upper semicircle, centered at the origin and having radius r. That's almost like a important subcase deserving its own spot in your memory. Example 5. What will be the likely basic graph shape of this function here? Okay, you notice the y equals 2 square root of quadratic expression. Begin the mental process. Square both sides. Move the x squared term to be with the y squares. You have the coefficients being same sign but unequal. That would initially remind you of an ellipse. The radical crops half of it. You've got a half of an ellipse coming up for a graph. That's indeed the case. Example 6. What will be the likely basic graph shape of this function here? Okay, once again, you start off by noticing it's y equals to the square root of a quadratic expression in x. Begin the mental process. Square both sides. Move the x squared terms to be with the y squared on the y squared side. They have opposite signs. Initially you think hyperbola. The radical crops half of that. You're planning to see half a hyperbola. And that's indeed the case. Okay. Now, something else. What if there was an x term in the quadratic expression? These first 5 examples were all a little bit especially simple. They just had some x squares and some constants, no x terms. Good news is, it makes no difference. The process and the conclusion is unfazed by this. Here's an example. What will be the likely basic graph shape of this function here? Looks a bit complicated, but the essence of it is a y equals to a square root of a quadratic expression in x. Begin the mental process. Square both sides. Just concern yourself with the x squared and y squared terms. Move the x squared terms over to be on the y squared side. Coefficients have the same sign, but are unequal. Reminds you of an ellipse. The radical crops half of that, and so you're thinking this will be half of an ellipse. Correct. Example 8. What will be the likely basic graph shape of this function here? Okay, you notice the essence of it, and that is it is a y equals to the square root of a quadratic expression in x. Begin the mental process. Square both sides. Keep track of just the x squared and y squares. Move the term over to the y squared term side. They have different signs for coefficients. You're thinking initially hyperbola. The radical sign has you thinking crop to half a hyperbola. Half hyperbola is indeed the case. Another issue. What if a negative sign appears in front of the square root? Okay, well, thinking back to, say, your study of transformations, if y equals to f of x is some function you're familiar with, and all of a sudden you read about a function g of x equal to negative of f of x, what's that? Oh, that's just a reflection of the graph of f across the x-axis. So this negative sign in front of a square root would do the same thing, reflect across the x-axis. However, you know that with these conic sections, the ones that are centered on the x-axis, they have symmetry with respect to the x-axis. So this reflection is actually just giving you back the lower half of the graph of that conic. Okay, so here's our answer to the question. If you have a negative sign in front of the square root, the graph will be one of the 3 choices, the lower semicircle, or the lower half of an ellipse, or the lower half of the hyperbola. Let's try an example here. Number 9. What will be the likely basic graph shape of y equals to this? Okay, you notice you see a square root of a quadratic expression in x. You see a negative in front of the radical sign, which you can almost ignore at first. You can account for it in your conclusion. Instead, you proceed to square both sides. Just worry about keeping track of the x squared term and y squared term. Move the x squared term over to the y squared term side. Coefficients have opposite signs. Now you would be thinking initially hyperbola. The radical crops half of that. You're thinking half a hyperbola. And then you can go a step further and account for that negative sign in front of the square root and say, oh, this will be a lower half hyperbola. There's the graph. And yeah, that's indeed the case. You got that lower branch of hyperbola in this case. Okay, now that you're aware of this, you could actually put the adjective upper and lower in front of all your future conclusions of these types to make a more precise description of the graph shape. Okay, something else. What if there is a constant added or subtracted from the square root at the very end? Okay, this is nothing too special. Just as with in your transformation studies of functions in general, it just causes translation up or down, depending on if the constant is positive or negative, respectively. Here's an example. What will be the likely basic graph shape of this function here? Okay, you notice the essential part of this as being the y equals to the square root of a quadratic expression in x. That plus 3, that'll translate it up 3 units, but just kind of ignore that for now and account for it when you make the conclusion. There's also a negative sign in front of the square root. Okay, so it's going to be a lower half conic section here. Otherwise, proceed, ignoring the plus 3, and square both sides. Just concern yourself with the x squared and y squared terms. Move the x squared term to be on the y squared term side. This would have equal coefficients, reminding you of a circle. The radical has you thinking semicircle. The negative sign in front of the radical has you thinking lower semicircle. And finally, the plus 3 translates you up 3. So we're expecting the graph to be a lower semicircle translated up 3 units. Correct. Okay. Now, let's go back to this generalization that we've been taking a look at here. It says the graph of a function of the form y equals to the square root of a quadratic expression in x will likely be... Oh, wait a minute. Likely. Did you notice the word likely there? Okay, so why does the word likely appear in this conclusion? Same as in your study of conic sections if you study them extensively enough. And that's it. There's always this chance that you're going to run into a degenerate case, and this leads us to this kind of situation for these radical functions. You could encounter a graph that is a single point, or a pair of rays emanating from a common point, or an empty graph. In other words, no graph at all, no points. All right, and again, the reason for this is based on the idea that when you square both sides of the equation and you're in the world of conic sections, you could be running into degenerate cases. And remember, the degenerate case of the circle, that's a single point. The degenerate case of an ellipse, it's the same, it's also a single point. The degenerate case of a hyperbola is a pair of distinct intersecting lines. So when these radical functions come along, they basically are cropping half of one of these 3 situations, and that leads to that other conclusion. Okay, here's an example. What will be the likely basic graph shape of y equals to all of this? All right, you notice, oh, there's a translation up 2 units there. You kind of note that and then ignore it and focus on this quadratic expression. You proceed with the process where you square both sides. Just worry about the x squared and y squared terms. Move the x squareds over to the one side. They have the same coefficient. Now, this reminds you of circle. The radical, you think semicircle. The plus 2, it's translated up 2 units. So we would normally conclude this to be an upper semicircle translated up 2 units. Oh, surprise! It's actually a single point. Okay, well, that's why we say likely in our conclusion, because there is the remote chance that this could occur. And it did in this case here. All right, and you don't know this until you work out the algebraic details and put it into a standard form and whatnot before you would realize this, most likely. But anyways, for a basic likely graph conclusion, we just are aware of the fact that this could happen. Example 12. What will be the likely basic graph shape of this function here? The essence is a y equals 2 square root of quadratic expression in x. That minus 1 on the tail end, that just translates matters down 1. Okay, kind of ignore that for the moment and proceed with the usual process. Square both sides, keep track of x squared and y squared. Move the x squared term to the y squared term side. Coefficients have opposite signs. So we are reminded of hyperbola. The square root sign is going to crop half a hyperbola. The -1 translates down 1 unit. Our likely graph will be an upper half of a hyperbola translated down 1 unit. Whoa, surprise! It's actually a pair of rays emanating from a single point. Okay, we've hit a degenerate case here in this example as well. Alright, this is extremely rare, but you do want to be aware that it could possibly happen. Example 13. What will be the likely basic graph shape of y equals to this expression here? Okay, it's a quadratic expression in x under a square root sign. Could begin the process. Square both sides. Move the x squared with the y squared. Now they have the same coefficient. This reminds you of a circle. The radical crops half the circle. We're thinking semicircle, upper semicircle in fact. The graph is empty. Okay, that could happen. And this is one of the special situations you could run into. And algebraically speaking, if you look at the formulation there, y equals to the square root of, now that radicand's got a negative of an x squared minus 1. So you've got a negative x squared, which can never be positive, and then you're minusing 1 on top of that. You surely have a negative radicand. You surely have got yourself an imaginary valued function. So no graph in the xy plane for this one. Okay. Fortunately, encounters with degenerate cases or no graph cases really are rare. I suppose you could go through all of the major calculus textbooks that are out there right now today. If you were to examine every single y equals to square root of a quadratic expression, I would be surprised if you even encounter a single degenerate case in all those books. Okay, ready for a 5-question quiz. You get 10 seconds for each one. Let's get started. Ready? Example 14. What will be the likely basic graph shape of this function here? Did you say lower half of a hyperbola translated up 2 units? Correct. Okay. Example 15. What will be the likely basic graph shape of this function here? Did you say upper half of an ellipse translated down 4 units? Correct. Okay. Example 16. What will be the likely basic graph shape of this function here? Did you say lower semiparabola, horizontal axis of symmetry, vertex at -4, 5? Correct. Example 17. What will be the likely basic graph shape of this function here? Did you say lower semicircle, translated up 2 units? Correct. Example 18. What will be the likely basic graph shape of this function here? Did you say upper half of hyperbola translated down 7 units? Correct. Alright, hope this has helped your ability to nearly instantly recognize the graph shape of these 2 subclasses of radical functions. It can really give you a lot of confidence in your math when you already can see through quite a bit of what's going on in a math problem without so much as lifting a pencil. Okay, congratulations. Exercise 41.13. This exercise is to be solved manually. Consider the region enclosed by the graphs of y equals 2, negative 1 minus square root of quantity negative x squared plus 6x minus 5, and y equals 2, negative x squared plus 6x minus 6. Part A. Sketch a quality graph of the described region. Provide a graphic approximation of the area of the region. Part B. Provide a calculus calculation that yields the exact area of the region. Part C. Assess the correctness of parts A and B by examining for consistency between the two results. Part A. Sketch a quality graph of the described region. Provide a graphic approximation of the area of the region. Let's try to figure out what sort of graphs we have here. For this function on the left, recognize this as being a function having the form y equals 2 a square root of a quadratic expression in x. So we can quickly predict the basic graph shape here, and it looks like it will be a likely lower semicircle translated down one unit. That being said, we will need more information to help us graph it, of course. And so then let's take this idea that we're expecting a lower semicircle and then rewrite this equation in standard form for a circle. Let's start off by doing that. Alright, at this point we have got our standard form of a circle here. Now, although we have the circle sitting here, we know from this earlier radical that we actually have a semicircle, and then we know from that negative or subtraction sign preceding the radical that we have a lower semicircle. So here it would actually be a lower semicircle, radius 2, centered at 3, negative 1. Alright, so about like so. Now this tells us we will be needing, let's see, a center at 3, negative 1 and a lower semicircle. This has us thinking, looks like quadrant 4 will have to be prominent in our graph. Let's go ahead and take on that other function and see what we think about that, rewriting it here. Alright, this is a quadratic function, and of course its graph will be a parabola. It will be a parabola opening downwards, and the x-coordinate of the vertex will be a negative b over 2a. The y-coordinate of the vertex, just substituting the 3 in there, 3. Okay, vertex at 3, 3. This is furthermore a translation of a y equals negative x squared. Alright, now let's see, this would give us something that is in quadrant 1 primarily. So it looks like we need some quadrant 1, quadrant 4 without very large coordinates in the x direction. Looks like we go out to about 4 or 5 or so and we'd have it. So let's take this information into account and sketch up a graph. Okay, so now we have, this is our enclosed region. Looks like we ran into the intersections of these curves just by simple graphing, so no problems there. It's at 1, negative 1 and 5, negative 1. Alright, as far as getting the area approximated for this region, we'll try to kind of get a simple geometric shape here drawn that sort of approximates things. Thinking trapezoid here. Right now I'm imagining this excess region to fill the voids I'm leaving here. It's kind of a little visual game here to play. Same thing up here. I'm going to have this little excess fill the little voids I'm leaving with this trapezoid. Okay, so now I'll make the statement that the area of the enclosed region is approximately that of this dashed line trapezoid. The area for a trapezoid is just a basic remembering that it's average base times height, so that'll be 1/2 b1 plus b2 times the height or altitude there. Good news is this graph has been sketched with the axes scaled the same, and so this makes for easy ruler measurements to get the bases and heights. First the bases. .4 and 1.6. The height or altitude looks to be 5.6. Let's see, what's this give us? This is let's see, 5, 6, half of 6. Okay, 3. 3 by 5.6. That'll be, let's see, 5, 10, 15 plus 1.8, 16.8 square units. Okay, I'm going to put this in a nice prominent cloud here since it is the conclusive statement to the graphic approximation. Part B. Provide a calculus calculation that yields the exact area of the region. As for sizing this region up for a calculus approach, I hesitate to go with the slicing method right away here because I'm noticing a semicircular region, and that would give me a chance to use some plane geometry, which is always simpler than setting up a definite integral. So the net area of simpler regions strategy looks like it's the way to go here, and I am kind of visualizing this region as being the sum of two simpler regions, one being a parabolic region and the other one being a semicircular region. Okay, and this will equal, well, the parabolic region part, I'll make that as a subcalculation. Let me put an asterisk there. And so I'll leave that alone for a moment, and I will here just take on the semicircular region that we can just obtain by using the fact that the area of a circle is pi r squared. So for a semicircular region, we'd have 1/2 pi r squared there, and we'll be able to move forward with that. But let's go ahead and work on this parabolic region here in a subcalculation, say right here. Now, one thing about this parabolic region is that since we know that that graph of the y equals to negative x squared plus 6x minus 6 is really a translation of y equals to negative x squared, this makes it really a very easy matter to translate this parabolic region to an easier location, really, and compute it that way. So we'll point that out to the reader. And that new location, which I believe would make the calculation as simple as possible, and I just a little hand sketch here because I'm not using this for any sort of graphic approximation, and that would be just to bring it over here to vertex at 0, 4. Like that. Now we can also use symmetry as well in this situation. And then we're just looking at the area under this curve type calculation. That's pretty easy for calculus. And this means that the area will equal, okay, symmetry being utilized. I'm just going to double the result we get from going from 0 to 2. And so 0 to 2, 2 times that result. This is, what would this be? This has to be the negative x squared, but it's been translated up 4. So that could be written as 4 minus x squared. And that makes our integrand 4 minus x squared dx. Okay, let's go ahead and get an antiderivative there we can do in our heads. Pretty easy. That'll be the 4x minus the 1/3 x cubed. Evaluate between 2 and 0. This will become 2 times. Okay, 4 times 2 is 8 minus 2 cubed is 8 over 3. The 0 evaluation just gives a 0 all the way across there. 8 and 8, okay, this is 24 thirds minus 8, 16 thirds. 2 times 16 thirds, 32 thirds. Okay, we can bring this back to our main line of solution here and make this 32 thirds. And so then this becomes 32 thirds plus 1/2 pi times the radius of that semicircle. There was a 2. So then 2's cancel. This gives us 2 pi. There's our quantity, and we can just put square units on here. And this is our calculus calculation. Okay, looking forward to the part C to check on all this to see if we think this is indeed the case. Part C. Assess the correctness of parts A and B by examining for a consistency between the two results. To assess our correctness, let's take a review of our graphic approximation. And let's see, that was we said 16.8 square units. Probably should have rounded that to 17 square units. It's a little strange to have a graphic approximation recorded with 3 significant digits, but okay, since we've already done that, we'll just re-record that fact here. And our calculus result is still in sight there. Let's turn that into a decimal approximation. Alright, so we have 10 and 2/3 here, so that's about 10.7. Okay, 2 pi, about 3.14. 2 pi's, 6.28. And this will be, let's see here, 16, about 17. Alright. Oh, this is really nice because with 16.8 and 17, okay, gosh, let's see, 1.7 would be 10%, and 0.17 would be only 1%. This is, okay, these two results are within 2% of each other. So that would make them surely consistent. And thus we believe that the solutions to part A and B are very likely correct. So there we are. This is really looking good with such a good agreement between the graphic approximation and a calculus computation. So there we were able to use the net area of some simpler regions to obtain this result. And we also made use of a translation idea to simplify the calculus calculation, which worked out quite well as well. All right, very good.